Swayam Prabha. Digital India. Educated India.
So let's do the non-prismatic column. And so Belinda is going to show later basically how we can introduce a taper. But I can basically go to a function and say, okay, I want to make this web tapered from one dimension. Here in this case, it's 300 millimeters total depth at the bottom, and it's linearly tapered up to 1,000 millimeters total depth at the top. But then all the other cross-section dimensions are what we just did. Okay. So what do you think? Do you think the flexural buckling out of plane on this is going to change significantly? Any bets? Now you can see up at the top, just to make sure I had a concentric axial compression here along the inclined centroidal axis, I gave it a component x and z and x for the applied load at the top. What do you think? Is the buckling load going to be larger or smaller? Or the same? You're not going to say.
Larger.
Larger. Let's see. So we'll run it. Buckling. 12. It was 11.97 before. All right. But what's 0.03 among friends, right? We look at, let me pick the right one there. And so we tone the S shape down there a little bit. Pretty much the same sort of buckling that we were just looking at, right? It's just now it's got a tapered web depth. Okay. So elastic buckling is pretty much the same. So now let's go to the non-prismatic column top verification. All right, so we can do this one really quick. So if you pull up that file, non-prismatic column top verification, everything kind of looks the same because I'm doing the top. Now remember the concept that I pitched to you that we're using in Design Guide 25, the AISC MBMA Design Guide 25, and we're using this concept also with some of the things that are moving forward to promote non-prismatic member design verifications in the 2027 ballot 2. The idea is, suppose that you are doing a buckling analysis to verify your design on some structure that had several columns. Now, if you apply the load, you do the buckling analysis, you can say, well, what's the load in each of those columns at buckling, right? That's your P critical or your PE, if you like, okay? All right, and then you'd say, okay, now I'm ready to check each of those columns. I've got I can say, well, what's the cross-section demand, a PU to a cross-section strength? We'll talk about that here in a bit. Actually, let me come back. It may be good to talk about that here if I don't have it there. Okay. All right, we'll come back to it over here. Okay. So for each column now, I've got an elastic buckling load, I've got a PU, and I've got some sort of a cross-section strength that I can quantify in terms of axial load. If you've got all those, you've got everything you need to then determine a PU over PPN, the design demand to capacity ratio for the member, for each member. So what are we doing when we have a non-prismatic column check? We're simply saying, okay, I've got this cross-section up there. I've got this buckling load. Okay, let me treat that cross-section. I've got my PU to cross-section strength at that cross-section. I've got an elastic buckling load level, or a gamma E if you wish. And so now I treat that cross-section as if it's a member. And say, okay, well, or if you want to say, I go to the spec and I say, I want to do I want to know what the strength is of an equivalent prismatic member that has that cross-section, that PU, and that gamma E, or gamma critical. Okay? And I say, well, okay, well, I've got that one, and I can move down. Okay, let me check this other one. Let me check this other one down here. And so generally, we would check in Design Guide 25, it basically says, okay, here are several locations that you should check, and you look for whichever one is going to give you the largest PU over VPN. Well, it's just like your column design when you design multiple columns in a building. If you're checking all axial loads, you'd check them all and say, oh, that column over there is most critical, right? So you're just treating a non-prismatic member like multiple columns. Okay, so it means we went to the top here, but the top cross-section is the same cross-section we were just working on. So nothing changes, except our gamma critical is 12 instead of 11.97. Everything is practically the same all the way through the bottom. Okay, so that's we've basically got our checks getting down to our demand to capacity ratio here, pretty much the same 1 to 3 significant digits. Okay, all right, so then now here I'm showing a cross-section check. Now what we came up with and worked with Balint and his colleagues at Consteel, and they implemented in Consteel, okay, can we identify what the most critical cross-section is? And so one way of doing that, it's not exact, but it gets you a reasonable estimate in general. We basically say, okay, well, let's do it the same way Eurocode does. We're going to calculate effective widths based on yield of the plate. So that's what you see here. So you see you're getting smaller effective widths because you're taking it all the way up to yield. Let's get an AES for the S for section. That would be my effective section if I were taking the cross section all the way up to yield. Then I can see now AES over EJ, my goodness, that's less than 40% of the gross area. This is crazy. And then I can do a phi PNS for a cross section, 0.9 FY AES. So that's what we use to basically gauge. Okay, let's do a cross section evaluation everywhere, and we'll identify the cross section in every member that has the largest PU to phi PNS, and we'll go there and say, okay, we're going to do we're just going to do one member check at that location, and we're going to take that as the critical cross section. It doesn't necessarily always land you on the one that would be the most critical, but it gives you a reasonable result. Even with this crazy cross section here, we're within like 0.03 of nailing the 0.262 at the top. Okay. All right. So and that check would actually send us to the bottom of the of the column, which is what you might expect on most tapered columns like this. If it didn't have crazy effective width reduction, you say, well, I've got the smallest cross section at the bottom. I would think that that's where I'm getting the largest cross section utilization, or the demand to capacity ratio, right? And so that's how it usually works, but this problem kind of does some crazy things because of the wild effective width reductions. All right, so that file's almost identical to the one we did for prismatic, but the only thing we changed was, okay, we're checking the top, and we went in with 12 instead of 11.97 for the eigenvalue. Any questions there? You know, I always tell my class at Georgia Tech, you have to ask me questions to slow me down. The real answer is you can call anything you want a member. You can say anything's a member. You can say this column is made of 100 members from top to bottom, or it's made of one. But then there's some there's some advice in terms of what you might want to do.
What will be the most optimistic?
Well, the simplest, I don't want to have to check 100 members, so the simplest would be I have one and I check it. But then there's some ramifications and some reasons why we're splitting the roof girder into 2 members. So we'll talk about that later. Okay? Yeah, best to leave that one for the, I think that'll be a good discussion later. Okay, so again, if we're using consteel, we would just go straight to the bottom. So I went to the bottom here, and so now at the bottom, D is just 300 millimeters. And so that changes, but everything else is largely the same. The gamma critical is 12 for the outer plane. And so we just carry everything through. The calculations are exactly the same, but we're doing it with a total depth of 300, and we get 0.233 at the bottom. Okay? And so in Design Guide 25, we'd say, okay, well, that one wasn't the most critical. We'll use the section at the top. But generally, we need to check also in Design Guide 25 where H over TW passes through 131. And so I did one other check for an intermediate point where I said H is 131 TW. What's the depth? So let's check that particular location along the length. And when we do that check, same calculations, okay, 2.244, that's a little bit larger. Okay? That confuse you? So that's the column. Checks. I see some frowns. Yesterday you were all nodding yes. We're good? Okay. All right. Now to wrap up this session, I want us to talk about the beam checks. So if we're wanting to get a demand to capacity ratio for flexure, it's very similar concepts. Okay? But of course the equations are different. And so here, let's see. Let me see if did I pull that up? Yeah, I've got it. Single member prismatic beam. So I've got 403 kilonewton meters applied as a moment at the top. Same geometry for basically using the cross section at the top. We can run the analysis, look at buckling, on the buckling mode down there a bit. So what's going on here? Which flange is in compression, in flexural compression? The one to the right, correct? And we can see that, so here we've got a moment diagram that's varying from maximum at the top linearly to 0 at the bottom. Okay? So we got high moment up in that 1.5 meter long top segment, and then smaller moment in the bottom segment. Okay? And the eigenvalue here is 4.83. So we're going to take that in kind of similar concept. So let me get the page zoomed up here. View, where's view? View, okay. All right. So if you're guessing that the critical cross-section for bending is probably at the top, that's a pretty good guess. And we could do multiple checks. I think I actually put in one non-prismatic beam. Oh, that's non-prismatic. This is prismatic. So yeah, so prismatic, clearly, yeah, the maximum moment is at the top. It's the same section throughout. The top cross-section has the biggest cross-section demand, right? All right, so we're just calculating a few miscellaneous parameters here. Moment of inertia, elastic section modulus. So now getting into the flexural provisions that I had shared with you yesterday. So this is doubly symmetric again. And so HCY is HC is equal to H if it's doubly symmetric. H is the distance between the insides of the flanges for a welded section. So 198 again. Then we have an A sub W parameter that in this case gives the ratio of the area of the web to the area of the compression flange. So that's 5.49. You think that's a big number? 5.49 is a very big number for, this is a huge web with us. Dr. Galambos used to call these as webs with top and bottom stiffeners. There's a small flange with this huge, deep, slender web. Okay? What's that? Galambos.
The Hungarian.
Galambos, yes, as a proud Hungarian, Dr. Vasilievich, did I say that fast enough to get through it? Vasilievich, yeah, right. And I screw up all your Indian names too, I'm sorry. Anyway, from Dr. Lakshmi Priya's work, we recognize that once we're getting into some of these sections, the slender web, or the non-compact web limit, where it goes from non-compact web to slender web for flexure, or class 3 to class 4 if you're thinking more in terms of Indian standard or Eurocode standard. It is not as, it's the very small flange, very large web is tending to be damming, and we need some reduction in that non-compact web limit. And so for grade 50 steel, in this case, the CRW is its minimum value of 4.6. The maximum value is 5.7. Currently, we would use 5.7 for everything. And so we get 110.8 if you have an H over TW larger than 110.8, it's a slender web, or class 4. So what does that mean? We get web local buckling before we can get to the yield moment. Now, in the Eurocode, we can set up and calculate an effective width of the web and get basically an effective yield moment for the cross section. R sub B in the new provisions is essentially the same equation as what's listed as RPG in the current 2022 specification that you have. PG was for plate girder, and then we basically said, oh, you could have a plate girder that's got like a really stocky web, so why are we calling it plate girder? It's a slender web member. And Dr. Ura and Dr. Glambos would never let us change that because people are used to seeing RPG, but I managed to sneak this in when nobody was looking in the latest in the latest version of the ballot for AISC. So the reduction on the yield moment accounting for post-buckling strength of the web here is 0.833. So that's a fairly large reduction, relatively speaking, but it's a very thin web. We can calculate the yield moment to the compression flange, and then this term M sub W is kind of like a cross-section strength. It's called the strength considering yielding and web local buckling. So here, that's what it is, yielding and web local buckling. The web local buckling and post-buckling is captured through RB. And so that's your so-called plateau strength. That's the maximum limit that we can use in our design. We reduce from that when we look at lateral torsal buckling or flange local buckling. All right, so now we need a flange local buckling resistance if this flange is class 3 or class 4. The compact limit in AISC, which is equivalent to class 2 in Indian code and Eurocode, we take 12, that would be 12.5 for this case. No, that's actually the actual B over 2T. The compact limit is 9.15, and so we're exceeding the compact limit, but the non-compact limit is given by this equation for flexure, KC is 0.35. That's 16.2, so we basically have a non-compact flange, or essentially class 3 in Eurocode or Indian code. And so the equation that is moving forward in the balance at AISC for the flange local buckling strength is what you see here. It's basically a linear reduction all the way out. There is basically a check that you'll never practically reach, where you basically say, I'm not going to allow that line to go less than the elastic buckling strength, but you'd have to have something really, really silly before you'd ever get there. And so 429 is the flange local buckling resistance, and that gives some accounting in a very, very, very simplistic way for post-buckling strength of the flanges in flexion. And you can see we're at 0.734 of the yield moment at the flange local buckling strength. Now in the AISC provisions, flange local buckling is basically handled as an independent limit. And so you do lateral torsional buckling, you do flange local buckling, and if you're short enough for your unbraced length, flange local buckling might take over at something less than the plateau strength for lateral torsional buckling. So here, let's look at lateral torsional buckling. We have a slender web, and so things get relatively simple in some respects if we have a slender web. The lambda P limit, that basically gives us the width of the plateau strength, is a constant regardless of any moment gradient for a slender web section, 0.35. This is exactly the way it's been in Design Guide 25 and the way it's been programmed in Consteel. The moment at which we consider that we transition from elastic lateral torsional buckling to inelastic, that's been lowered, however. It's 0.7 MY in the 2022 standard, but we argued until we were blue in the face of, look, here are all these experimental results. It's saying that's going too far. This goes all the way back. Lakshmi and I were arguing with folks about this back at the beginning of time. So I think we finally have some traction where that reduced ML is moving forward in the standard. And so lambda R LT, if you look at kind of how that's working, that's really just square root of Fy to the elastic buckling stress at lambda RLT. So that's 1.414. Okay, basically square root of 1 over 0.5, or square root of 2 in this case. All right, we had the 4.83 from Consteel for the lateral torsional buckling. So we multiply mu by our elastic eigenvalue to get to the moment at the top of the column at elastic buckling. Now, if you caught what I was showing you last Thursday night, or what I showed you a little bit yesterday with the flexural provisions that are moving forward, in the current AIC specification, if it's a slender web, we calculate lateral torsional buckling strengths taking J equal to 0. We don't account for any contribution from St. Venant torsion. I think AISC and the U.S. bridge standard are the only in the world that are doing that. We're moving away from that to always calculating the elastic buckling resistance with both St. Venant torsion resistance, GJ, or I guess it would be GIT for you, is that right? And G is the shear modulus, is that right? Okay, all right. And the warping rigidity, we call it ECW, you call it EIW, is that right? Okay. So all those terms go in, we calculate the strength. The painful side, I think, in many situations is we need to do some extra work to calculate another reduction factor, because we've seen from analytical work validated somewhat by experimental testing, but the experimental testing has been mainly inelastic lateral torsional buckling. We're seeing that the distortion of the web exacerbated by shear can be a significant attribute in reducing your elastic lateral torsional buckling strength. And so my colleagues at UT Austin have done a lot of good analytical work to come up with a factor to address that. It's called CMV. And so particularly if we're looking at a non-prismatic beam, it's, oh my goodness, I've got it. Belinda already doesn't want to calculate CV, and now we need to calculate a CMV on top of that. And so we're, compared to just taking J equals 0 and calling it a day, it's a little more work. So here, in the interest of using Consteel with the way it's programmed right now, in the interest of not taking a lot of time walking through that additional part, we're just going to do it with J equals 0. That's what was done in Consteel with getting this gamma critical out of plane. So RB is being used as a surrogate for a lateral distortional buckling factor for the elastic buckling range. So, yeah, so it's actually derived from web bin buckling, right? But you know from the work we've done, we basically said, hey, yeah, go ahead and throw it on the elastic buckling, and it kind of makes things better, even though it doesn't have a basis for doing it. Yeah, so the research team at UT Austin developed a separate lateral distortional buckling factor, but they've taken it under advisement that something's not quite right with the way that equation is working. It kind of does some very weird things. And so in the meantime, we're using RB as essentially a surrogate for a lateral distortional buckling and uniform bending. Okay, but before we'd take RB or RPG and a J equals 0 and knock it down. Now it's include a J and we only reduce it by RB. Okay. So I think it's better if you have something like you're checking an erection scenario and it's super long. The St. Bernard torsion can help you quite a bit there, but if you've erected something super long like that, you know it's kind of deflecting like a spaghetti noodle anyway, so you need to be careful either way. All right, so I think we're just about to wrap up. I want to do this, and then we can do a quick run through, okay, how do we do non-prismatic? And then we'll take a break. So here we have a gross cross-section DCR that we're going to calculate. So that's 0.69. And so we use that to get a lambda LT, square root of my to the compression flange over elastic buckling moment, or we can write it as FYC over, or Fy of the compression flange divided by elastic buckling stress. Same deal. Or, in general, we write it as 1 over the elastic buckling eigenvalue over the demand to capacity ratio for the gross cross section, mu to my. So 0.548 is where we are for both. Remember, 0.35 is plateau for a slender web section. So here's the LTB equation. We got 441 kilonewton meters, and so 75.5% of the yield moment. And we can see the flange local buckling here is about 3% smaller than the lateral torsional buckling moment. So, all right, that's our lateral torsional buckling moment, but we basically chop it off at the neck and say, no, you can't get that high. Flange local buckling governs. And so the phi-mn is the smaller of those two, 0.9 times the smaller of those two, 386. And so you can see here now, oh, we're already over with moment, about 4% over. All right, so any questions there? So the next file is non-prismatic beam top verification. And if we go to the Consteel solution here, so I've now tapered the web, 1,000 deep at the top, 300 deep at the bottom. We're going to apply our moment here. 403 is the moment that we need to design for. And we'll scale that down a little bit to the buckling calculation. Okay. And turn that off so we can see the member better. So this is showing basically how things deform in our hidden line view. If we go to like just a wireframe view, we can kind of see how the cross sections are moving there with the lateral torsional buckling. Maybe that's a little easier to see. Okay, and the buckling load went down. So this shallow depth in the bottom is hurting us in terms of elastic lateral torsional buckling strength. All right, so let's basically say, let's suppose that we'll figure that the top is the most critical. So it's the same cross section we were just working with the prismatic member I just showed you. So this file is largely the same, except when we get down here to gamma critical for out of plane, it's 3.47 now. So it's reduced from what we had for the prismatic member. And then if we scroll down, okay, so now the demand to capacity ratio for the member is 1.07, where it was essentially 1.04 before. And I thought I did, maybe I thought I did something and then forgot and didn't do it. Just for a quick illustration, taking more of the Design Guide 25 approach, I'm basically, let me check the cross section at the girt. How do things look there? And so my H is 700.31 for the depth of the web at the girt. And if we work through everything, it's the same calculations, but just done with the shallower web. Same gamma critical. And so again, what are we doing? We're saying, basically, the simplest way to put it here, I want to check the strength of an equivalent prismatic beam that has the same MU to MW, if you wish, as this cross section, and has the same gamma critical. And so that prismatic beam is now a surrogate for checking where am I here at this middle cross section. Just did the same thing for the top. Obviously, if we go at the bottom, the moment is 0 at the bottom, so there's no need to check the bottom, right? So that's all this is doing. Oh, I get 0.918 here at this section. Now, oh, okay, I know why I didn't. So when we do the calculations in Consteel, if we were just checking moment, we look for where is MU to, essentially MU to MW, or MU over phi MW, where is that largest? Oh, that we identified it as our critical cross section. That's where we do our calculation. That usually does pretty good for beams because of some of the silliness of the way RB works with the equations. You can sometimes get other cross sections that actually give you a little bit larger demand to capacity ratio for the member checks, but it's not significantly different. All right, so that's pretty much, hopefully that makes what I think you've been puzzling with about notation maybe a little bit better. Okay, how do we apply these things to do design verifications? There we just kind of did it multiple times. That's the nice thing of having non-prismatic checks, is you have to keep doing them over and over and over and over, and then you put it into some software and have it do it, right?